In this video, I'm going to explain a couple of the harder problems on worksheet 7. Sometimes people struggle with problems such as 15 where they have to determine the value of n. What you want to do for a problem like this is first decide if it's arithmetic or geometric, and then after you've done that, you know which sum formula to use. In this problem, we tell you that it's an arithmetic sequence, which is how we know we need to start with this formula. Always start with the formula that you want to use to finish the problem, and then work backwards to fill in what you don't know. We know that our first term is 3.5, so we can put that in right here. What we don't know is our nth term. So to find our nth term, we can use our explicit formula, a sub n equals a1 plus n minus 1d, and simplify to get an expression for a sub n. Once we have that, we can plug it in, and now we can go ahead and work on the algebra. At this point, when we get to here, where we have a quadratic, we can either solve this with quadratic formula, factoring, or polynomial. We want to use some common sense and remember that the values for n have to be positive whole numbers. We can't have any fractions or negative numbers because that does not make sense for this type of problem. If we look at number 16 is a similar problem compared to 15, except now we are working with a geometric series. The problems with geometric series are often a little bit harder just because the formulas are more complicated, but we're going to start the same way. We're going to start with saying I need to find a finite sum for a geometric series, and then we plug in everything that we know. We know the value of the sum, we know the third term and the sixth term. So if we have the third term and the sixth term, we can go ahead and we can express those terms like for example, we can get that the third term is a1 times r squared. We know that our sixth term is equal to a1 times r to the fifth, and we can use some of those techniques we've been talking about in class to work backwards and solve for our r value and our first term. Once we know our r value and our first term, we can plug into our formula. Now there are a couple of very important things we have to look at here. The first thing that I want to refresh your memory on is that we have to have the r value in parentheses when we are raising it to the nth power. If r happens to be negative and n is a positive number, that negative sign gets wiped out. If n is an odd number, then that negative sign remains. And at this time, we don't know if n is positive or negative. So we're going to make sure we put parentheses there. Now what we want to do is we want to go ahead and unpack this problem. We want to take care of everything all around it. We are going to simplify the 3 and the 5 and multiply the other side, and that's how we get the 262,145. We minus the 1 over, we divide off the negative sign, and then we get to this point right here. Now at this point, since we have negative 4 raised to a power equals a negative value, that tells us that n must be odd. So now we can focus on just what power of 4 gives us 262,144. We can solve this by logs, by rewriting in log form, and then the way we enter this in our calculator is log 262,144 divided by log of 4. We can also guess and check our powers of n at this point. Looking at problem 18, the first thing we have to analyze is whether or not we're dealing with arithmetic or geometric. And the keywords in the problem that help us know we are dealing with geometric is that it says each subsequent minute, meaning each next term, he can eat 3/7 as many hot dogs as he did in the previous minute. So that tells us that my r value is 3/7, and we know that in the first minute he ate 28 hot dogs. Now the other guy, Joey, similarly we can find out that his r value is 1/3 and 30. And we read through the problem and it finishes with saying if this is continued for as long as possible. That means if the rate of hot dog eating slows down the way that it says, eventually they're not going to really be eating any hot dogs anymore. So we're looking at an infinite sum. Since our r values are between 0 and 1, the infinite sum exists, and we can use the formula that the infinite sum is equal to a1 over 1 minus r. And we go ahead and we solve this for each of them. We get 49 hot dogs for Kobayashi and 45 hot dogs for Joey. And the question says if they're both allowed to keep eating for as long as possible, how many more hot dogs does the winner eat? And that's why the answer is 4 more hot dogs. In problem 19, we are looking at an arithmetic sequence. We are told that we get docked $4.25 for the first dish we break, $7 for the second dish we break, $9.75, and so on. If you subtract these terms, we end up finding that the difference, the amount that is added each time, is $2.75. So we start by figuring out the actual wages, and if we work 8 hours a day, for 5 days and we make $9.50 an hour, we would earn a total of $380 in a week. So the question is, how many dishes can we break before we lose our entire week's wages? So we're looking at, when does our sum of money deducted be greater than or equal to how much we made? So we're looking at, when is our sum greater than or equal to 380? From here we want to set up our sum formula. Because it's arithmetic, we are using the sum formula n divided by 2 times a1 plus an. We can fill in our a1 that we know, 425. Just like we did in the problem a few minutes ago, we can get an expression for the nth term by using our patterns we have talked about, a1 plus n minus 1d. And then we can go ahead and simplify. Solving the quadratic, we get two answers, 15.6 and negative 17.7. As we've already mentioned, we can't go backwards, therefore the terms can't be negative. So 15.6, if we, there's two answers that we can go with here, and either 15 dishes or 16 dishes. And the question says, how many dishes can you break before you lose your entire week's wages? So if I were to break 15 dishes, then my sum is still going to be less than 380. If I were to break 16 dishes, then my sum is going to be greater than 380. And that's why the answer to this problem is 15 dishes. Remember that we are not doing problem 20. We took induction out of the unit this time. That's not always the case, but we did do that this year. Good luck.